So this is the diagram of the practical Q meter. Sorry for the interruption caused by due to unnecessary calls. So this is the practical Q meter. In input side, you will be having the wide range oscillator with a frequency range of 50 kilohertz to 50 megahertz. That is used as a power supply to the circuit. And the output of this oscillator is shorted by the low value shunt resistance RSH. It is usually in the order of 0.02 ohms. So it will not introduce uh, any resistance, means it will not introduce almost no resistance into the oscillatory circuit, and represents a voltage source with a very small or almost negligible internal resistance. So this is what your internal input to the practical Q meter, which is having the wide range oscillator which can generate frequencies from 50 kilohertz to 50 megahertz, which will be used as a power supply circuit, having the small internal shunt resistance RSH, which is usually in the order of 0.02 ohms, which introduce almost no resistance into the oscillatory circuit, which represents the voltage source with a very small or almost negligible internal resistance. And the voltage across this low shunt resistance is measured by the thermocouple meter. The voltage across this low shunt value of resistors RSH will be measured by the thermocouple meter, and it is marked as multiply Q by meter, and the voltage across the capacitor VC, here you see EC or VC, is measured by the electronic voltmeter. So this is at the input side, and this is at the output side. So you will be having the at the input side, you will be having the voltage across the shunt resistance RSH is measured by the thermocouple meter, marked by the multiply Q by meter, whereas the voltage across the capacitor, that is at the output side, that is EC or VC, is measured by the electronic voltmeter. So in between this input and output, we are placing the unknown coil, for which we have to measure the properties of the electrical characteristics, such as your Q factor. So for making the measurement, now the operation of this circuit. So at the this we have discussed about the input as well as the at the output. So at the input we will be having the multiply Q by meter at the input, and we are having the electronic voltmeter at the output across the capacitor. And we are for the actual measurement, what we are doing, we are placing the unknown coil, whose test terminals are uh, here you see test terminals, these two dotted terminals. So this is the unknown coil having the resistance R and inductance L, and which is having the unknown stray capacitance of CD. Now what we are doing is, so as we have already discussed, the Q meter works on the principle of the series resonance circuit. So on the series resonance circuit, what we have to take, that is the total impedance will be equal to the resistance, and the capacitive reactance will be equal to inductive reactance. Both will be cancelled out. So what we have to do in the operation of the circuit, the measurement to be taken for the unknown coil is connected to the test terminals. Suppose these test terminals of the unknown coil, we will calling it as A and B. Then this circuit will be tuned to the resonance. Then this circuit will be tuned to resonance either by varying the oscillator frequency or by varying the resonating capacitor C. So you can now what you have to do, you have to as we have already know that Q meter works on the principle of the series resonance. So for the series resonance to be happen, we have to either by vary the oscillator frequency or by varying the resonating capacitor frequency. As we have indicating, resonating capacitor is variable, we can vary the resonating capacitor frequency or the oscillator frequency. So by using of this we can have the series resonance. When the series resonance happens, then we have to measure the readings of the voltage across the capacitor C and the shunt resistance RSH. So both the readings are obtained, that is the voltage across the capacitor as well as the voltage across the shunt resistance RSH. Then your Q factor of the coil is determined by Q equal to EC by E. Q equal to EC by E. So that is the how we are measuring the quality factor uh, by using this practical Q meter. So by resonation of this circuit, either by varying the frequency of the oscillator or by varying the resonating capacitor, we are making the circuit to be in series resonating condition. Then we have to make the readings of the voltage across the capacitor EC and the voltage across the shunt resistance E. Then your Q factor of the coil is determined by using the formula Q equal to EC by E. And this the Q, Q of the measured coil actually is greater than the value indicated by the circuit Q meters. So whatever the effective Q of the measured coil, effective Q of the measured coil is greater than the circuit Q. Why? Because there is losses in your oscillator and that is capacitor, resonating capacitor in voltmeter. So there will be losses in case of the in your oscillator circuit, in your resonating capacitor circuit, in your coil also you will be having the losses. That's why the effective Q of the measured coil will be greater than your whatever the measured circuit Q meters. So whatever the Q factor that is measured will be called circuit Q, but the actual measured Q will be greater than this circuit Q. Why? Because there is losses occurred while measuring the Q in the resonating capacitor and in the voltmeter, like that. So this difference is very small and may be neglected except when the resistance of the coil under the test is relatively small in comparison to the shunt resistance. This is the condition. So this difference will be usually very small and may be neglected except when the resistance of the coil under the test is relatively small in comparison to the shunt resistance. So you can calculate also the effective inductance and capacitance from the series resonance formula, that is XL equal to XC. You will be having omega L equal to 1 by omega C. From that you can calculate your either frequency or capacitance or inductance, and your quality factor is Q equal to VC by V. So here we are having the in the practical Q meter we will be having the wide range RF oscillator whose frequency is varying from the 50 kilohertz to 50 megahertz. A thermocouple meter that we are calling it as marked as multiply Q by meter. A calibrated variable capacitor, resonating capacitor, and last one is you will be having the actual Q meter. So here the description that we have already discussed: RF oscillator having the 50 kilohertz to 50 megahertz connected across the shunt resistance, which is giving the constant supply, as this one is very small. So that one the voltage across the RSH is calculated by the multiply Q by meter, and electronic voltmeter is used to mark as actual circuit Q meter. Unknown coil is inserted at the test input between the terminals A and B, and your CD is the unknown capacitance, that is stray capacitance. you can make this circuit to the resonance by either varying the oscillator frequency, that is principle of operation is by maintaining the E constant. You have to change the either this is the phasor notation, that is not required anyway. For series resonance you will be having Xc equal to XL, a capacitive reactance will be equal to inductive reactance. For this to happen, you have to change the either oscillator frequency or resonating capacitor, we have to change, so that this circuit will be under the series resonance. Then you will be having the Q will be equal to Xc by R, XL by R, so you will be having the EC will be equal to Q times the E. So that is EC will be measured across the circuit Q meter, but actual Q meter will be having the higher value than this circuit Q meter due to the losses in the resonating capacitor and the oscillator and voltmeters. So measurement of the Q connect the unknown. So note down this circuit Q meter, note down the value on the multiply by Q meter. So we have already discussed. So indicated Q will be EC by E, circuit Q meter reading by multiply by Q meter. So adjust RSH voltage to be unity, then indicated Q will be equal to circuit Q. So we have learned about the various testing instruments of the electronics, basic concepts of the quality factors of capacitors and coils. So and we have also construction and working of the Q meter and measurement of the Q factor. So say a simple quiz. Q meter measures the following: it will measure the inductance, capacitance, Q factor. So it will measure all the electrical properties of coils and capacitor, that is inductance, capacitance, mutual inductance, and quality factor and dissipation factor. So it will measure all the above. So ideal inductor has the high quality factor. Ideal inductor has the high quality factor. Bandwidth of the resonant circuit is, so bandwidth is inversely proportional to quality factor. So option is 2. Q meter operation depends on the series resonance circuit. So as it is depends on the series resonance circuit, option is this one. The value of shunt resistance used in Q meter is, as it is very low, to get the no almost nil resistance across the oscillator, it is 0.02 ohms. So there are different questions that will be asked in this one, that is list different types of test instruments used in electronics, list the applications of various test instruments, define quality factors of coils and capacitors, define dissipation factor, explain the construction and working of Q meter with this circuit diagram. Thank you everyone.